Let's. Okay.
Good afternoon, I'm Olivia Valiant.
I'm David Flores.
And I'm Oren Edmonston.
And tonight we will present to you our research, Swimming with Innovation, Engineering Inspired by Shark Skin.
All right, so to introduce this subject, humans aim to shape and optimize nature for their benefit. Biomimicry studies allows us to do this by looking at natural designs to solve real-world engineering problems. Shark skin, for example, demonstrates drag reduction and structural optimization. Reducing drag could significantly decrease operational costs across multiple industries. Next slide, please. Biomimicry. Biomimicry applies to the biological strategies to human technology. Shark skin is an example of naturally evolved drag reduction surfaces. Nature creates optimal solutions, right, under resource constraints. This is a definition of engineering. Engineering draws inspiration from riblet structures found in aquatic creatures. Next slide.
So before we continue, let's pause and see what exactly is a riblet structure. Riblets are tiny groove-like structures that are inspired by the dermal denticles found in shark skin. They align with the flow direction to manipulate the boundary layer and reduce turbulence near the surface. Key features include riblet height, spacing, and shape. This typically is optimized with a height to spacing ratio of about 0.5. As a result, riblets stabilize flow, reduce skin friction drag, and improve aerodynamic and hydrodynamic efficiencies.
So we're going to look at the shark skin efficiency now. We're looking at the reduction of surface drag under turbulent stress. The riblet-like microstructures do disrupt the turbulent flow patterns, which is really important to note. The textures also prevent microorganisms attaching themselves to the skin itself. And lastly, the applications could include cleaner medical devices in the future, as well as faster marine vessels.
All right, so hydrodynamic function of shark skin. This is interesting. Study by Auken and Luder tested natural skin on different surfaces. To sum up their findings, they basically found that flexible shark skin improved swimming speed by 12.3 as opposed to rigid shark skin plates, which their rigidity didn't allow any movement, so it created negligible drag improvements. This shows that drag reduction properties depend on flexibility and dynamic movements of surfaces. Next slide.
So for the orientation of the shark skin, the riblet orientation does affect the flow efficiency. The optimal riblet orientation increased the efficiency up to around 9.5%. The dynamic adjustment of riblet direction is crucial for the best and optimized performance. And lastly, the flexible surfaces on vehicles, such as submarines or other aquatic vehicles of the like, are needed to fully exploit the riblet advantages of this technology.
All right,
next we'll go over the synthetic riblet surfaces. So synthetic riblets mimic the dermal denticles on sharks. The ideal riblet surface are hydrophobic and flexible. The current synthetic riblets show a 7% improvement, however, this still lags behind natural shark skin. So to continue, man-made surfaces must innovate to match the natural adaptivity.
all right, so to tie in everything together, microbubbles reduces drag by 10 to 15%, combining that property with super hydrophobic riblet surfaces will increase energy savings. And couple that with flexible adaptive members, this could optimize these effects even further. Future designs may integrate multiple drag reduction strategies simultaneously.
Next, we'll cover bio-inspired innovation. There are 4 main industries that we'll cover. First is the aerospace industry. Riblet films, like AeroShark as shown in the picture, reduce drag on aircraft wings and fuselages, improving fuel efficiency. Our second industry is the automotive industry. Riblets are used on race cars, on their spoilers and undercarriages to minimize air resistance and boost their speed. Thirdly, we have the marine industry, in which riblets are used on the hulls of ships and submarines to reduce hydrodynamic drag and improve propulsion. And lastly, and most interestingly, it can be used in medical situations. So the shark skin inspired microtextures resist bacterial adhesion, enhancing hygiene on medical devices and hospital surfaces. This can be anything from the needle that you use to a door handle.
So for the manufacturing challenges, the complexity of the actual shark skin is very difficult to replicate in the real world. The traditional molding methods such as die casting, for example, lack the ability to get this complete surface detail and definition that we want to see in our technologies. The full replication of the shark skin denticles remains very challenging, and the mass production does need improvement to maintain performance at this scale of ability. So that goes into the 3D printing, which is probably the future of this type of production. We're talking about the resin 3D printing, which can actually replicate the level of intricacy that the riblets contain. And as you can see here on the second bullet point, we have the materials laid out. All that is just to say is the different materials that do make up the resin itself in different percentage-wise amounts. The 3D models are based off of the electron microscopic images of real-life denticles. And lastly, the future of 3D printing may allow the realistic scalable shark skin manufacturing of surfaces that we want to see in the future.
So to innovate and to manufacture effectively, we need to understand the mathematics that go behind riblet structures. So shark skin evolved riblet structures to stabilize turbulence and reduce drag. The riblets manipulate the boundary layer, reducing skin friction and drag for more efficient movements. So to analyze these phenomena fully, we have three main equations. You have your drag force equation, your skin friction coefficient equation, and your drag reduction percentage. This is effective for optimal scaling for viscous wall units. Second, to continue, we have to look at riblet mechanics. There are three main definitions here that need to be understood. First, you have secondary vortex formation, in which riblets create small vortices that suppress larger turbulence. Second, you have the dampening cross flow velocities, where riblets reduce turbulent velocity fluctuations. And third, you have effective protrusion height. This is where riblets thicken viscous sublayer without destroying the main flow. So after you understand these definitions, then we can go into scaling the shark skin up from its micro surface on shark to innovative technologies in which we use scaling parameters. These equations will allow the comparison across different flow conditions, and the riblets must be correctly sized to turbulence scales for maximum drag reduction.
In conclusion, the shark skin biomimicry offers the real world efficiency improvements. 3D printing does offer an advantage in the future for manufacturability and practical use. The future engineering will integrate the biological optimization into the designs that we want to see. And this will further close the gap between nature and humanity's improvements, which are now going to be achievable.
Thank you.
Yeah.